Thank you for the opportunity to talk about some of the work we've been doing over the years. What I've done here is kind of taken a talk I used to present the spectrum of tools we've built over the past 6-7 years for supporting quantum computing, which we put in a big push about 4 years ago to generalize all of them to QuDit systems. And so I'll give that overview and mention what dimensions they work in. Typically, it'll be restricted to QuDits that are prime dimension, so systems composed of prime dimensional QuDits. So just to give an overview of the kinds of things I'll talk about today, well, first I'll give some motivation and background, some of the math background, which is new for some of you, perhaps, and will be familiar to some of you as well. And then I'll talk about some of the really basic stuff around benchmarking components of your quantum computer system. So the advantages and disadvantages of the different approaches that have kind of emerged as standards. As an interlude, I'll talk about randomized compiling. So I guess I don't need to call it an interlude, but it's a break from everything else is about really error diagnostics and benchmarking, and randomized compiling is about suppressing errors. So I'll explain how that works and then explain also how it's actually an ingredient in some of the more advanced error diagnostic routines. Then I'll talk about cycle benchmarking, which is benchmarking parallel gate sets in a quantum processor, and some of the capabilities that derive from that, as well as reconstructing details of the error model across such systems. And then last, I'll talk about system level benchmarking. So that's benchmarking the kind of holistic performance of a quantum processor and addressing a really important challenge, which is this challenge of understanding when quantum computers give us incorrect answers. So, I feel like this is something people haven't really thought much about, haven't worried much about, rather. And it's especially beyond the scientific community, the broader business community, I don't think has understood how error-prone quantum computers are, even in the fault-tolerant limit. So I'll talk about that problem and some tools that we've worked on to help address that. Okay, so so here is actually the setup for that last bullet point. So, we all know this term NISQ that John Preskill coined. What is it? Noisy intermediate scale quantum computers. It's well understood that those quantum computations have errors now, and we need to think about what can we do in the presence of these errors. But the very fact that people emphasize that tells me that they haven't fully appreciated that this is actually just a problem of quantum computing. So fault-tolerant computers are not tolerant of all faults. Error-correcting codes are devised to correct certain classes of errors, typically low-weight errors. Physical error models always have high-weight errors. They will be small, one hopes, on some local assumptions of errors, but ultimately they'll be error-prone. So when we run quantum computations on a fault-tolerant quantum computer, there will be a failure rate, which will be difficult to predict and characterize. So we need tools to help us understand when we can trust the answer of the quantum computer. I think another reason this hasn't really penetrated the mainstream consciousness is because, we think about things like Shor's algorithm, where we'll know if the quantum computer gives an incorrect answer because we can efficiently check a solution that's put forward for factoring numbers. So, but for many of the cases where we expect to use quantum computing that are nearer term than that, quantum dynamical simulation, quantum chemistry problems in drug design and so on, these are all problems when we're looking at solving a problem like the binding energy of a protein and a lipid, and we don't know, and the quantum computer is going to spit out some answer. It's going to say, here's the binding energy, it's 10 millielectron volts. And the question is that, first of all, correct? And if it is correct, what is the error bar on that? Is it 10 millielectron volts plus or minus 0.1 millielectron volts, or is it 10 millielectron volts plus or minus 100 millielectron volts, right? So where do we even start to coming up with ways to bound the accuracy of quantum solutions so that they can actually be useful? And remember, fault tolerance is not going to be the solution. The other thing about fault tolerance is to realize that the errors it can correct are driven asymptotically to zero. That means in the limit of infinite qubits, the threshold, if you're below threshold, you can drive the correctable errors down to zero. but we're not going to have infinite qubits. We're going to have finite numbers of qubits. So a lot of reasons to be kind of wary of what is ultimately a great marketing term. Fault tolerance is a little bit of a misleading term for many. So this is probably pretty basic for all of you, but just to kind of set, unfortunately I should have generalized this to QuDits. We can replace the 2 with a D here, a lowercase d meaning dimension of the qubit. But we know that quantum computing power grows exponentially as d to the n, where n is the number of qubits. It's important to realize that the number of error modes, the number of parameters required to characterize an error model, grows 4 times faster in terms of the exponent. So it's d to the 4n. So just to think about the enormity of that number, if you have 50 qubits, which is already, state of the art is beyond that, you're looking at 2 to the 200 parameters in your error model that you need to worry about. That's comparable to the number of atoms in the galaxy. So it's just an astronomically big number. And we really need to get a handle on how to come up with the most relevant information that helps us move forward with kind of supporting experimentalists in the design of their gates, their pulse optimization strategies, and application-based work to understand the accuracy of the solutions for the application. So just to throw out some love for QuDits, given the theme of the conference, I just wanted to highlight some of the things that get me excited about QuDit systems. So if we're dealing with QuDit systems, it can provide a much more natural mapping of different physical systems we want to simulate onto the quantum computer. I'm just giving some example results in that area. But spin systems, high energy physics systems, atomic interactions, and so on. There have been several results showing that quantum error correction can be more efficient in the sense of lower overheads if we have d-dimensional systems. And just to highlight one of my own results from years ago, where we show that basically there's a natural relationship between what it means for a quantum system to be truly quantum, as was brought up in the last talk, and what it means for a quantum system to deliver a quantum computational advantage. So just to highlight what that is, it turns out that you can construct contextuality proofs, which contextuality is kind of a fundamental notion of non-classicality. It's a generalization of the Bell inequality. You can construct such proofs with basically stabilizer qubits. So Clifford-based stabilizer operations, or Clifford-based operations generate these kinds of non-classical effects for qubits. But when you go to QuDit systems, and in particular odd prime dimensional qubits, then what we showed in this paper is that there's a very clean separation between everything you can generate with the Clifford group is basically completely classical. There's no entanglement, there's entanglement, but there's no non-classical entanglement. There's no contextuality, there's no violation of Bell inequalities. And it turns out that also defines a threshold for getting speed up with quantum computation with odd prime dimensional qubits. So there's a lot of interesting things going on in this landscape of qubits. So now in terms of background, let me talk about a little bit of mathematics I'll be referring to throughout the talk. So when we talk about, obviously, a quantum transformation, the first thing we think of is a unitary transformation. But when we think about imperfections in implementing that unitary due to coupling to an environment, due to imprecision or fluctuation in the quantum control, then we have to worry about more generalized classes of errors, more generalized classes of maps. And the usual structure for that is the Krauss operator representation. It's probably the simplest thing everyone learns first. And there's also a little bit more advanced is this chi matrix representation, where the B operators, B sub alpha and B sub beta, are an operator basis for the set of linear operators of that system. But my favorite representation, which is, I think, the easiest to work with and the most intuitive, is this Liouville representation. So then you think about a quantum map, a quantum completely positive map, as you would normally represent with a Krauss form. Let's call that lambda. So it's taking density operators, which are elements of the bounded operators on the Hilbert space, to density operator sigma on the Hilbert space. The idea is we can expand, just like you can expand a qubit density operator as a sum over identity x, y, and z with coefficients. you can similarly expand any dimensional quantum system across a basis of operators that are a generalization of the 2-qubit Pauli operators. And I'll talk about natural generalization for the QuDit system shortly. And then you have these expansion coefficients B alpha, lowercase b alpha. So these are given by that trace rule. It's essentially the expectation of B alpha if B alpha is Hermitian. So I dropped the dagger, assuming B alpha was Hermitian, which it won't be for QuDits. And then the important thing to realize is that that's an inner product. So the inner product between two linear operators A and B is given by the trace of A dagger B. So A is in the dual space and gets a dagger, and B is in the base vector space. So what this means is when we look at this representation for lambda can be represented then by this trace rule B alpha lambda B beta, which gives us a scalar, a complex number, and that forms a matrix. And then we can think about evolving the coefficients of the input state rho into the output state sigma as just a matrix applied to these coefficients. And the beautiful thing about this matrix representation is that it composes the way you would expect things to compose in time. So if you have quantum operations lambda 1 and lambda 2 sequentially, then the matrix representing the sequence of those two operations is just the product of the matrices. Now, if we choose that basis to be the Pauli basis, this is called the Pauli transfer matrix. And so if we go to the PTM matrix and we think about some transformation lambda, then there's a nice decomposition where the lower right matrix of dimension 2 to the 2n minus 1 by 2 to the 2n minus 1 is basically a rotation matrix acting on the Hilbert space. Now, if we generalize this to d-dimensional systems, or QuDits, we have what are called either the generalized Pauli operators or the Heisenberg-Weyl operators. And here we have x as a raising operator. It raises the state, the basis state j by 1 modulo d, which is the dimension. I should have used a lowercase d here. I try to use capital D for the full Hilbert space of a composite system. But for the base system, let's call it capital D in this context. And then you have the z operation, which adds a phase. And the increments of that phase depend on the dimension of the QuDit. And then there's a simple commutation rule between z and x, which is a slight generalization of the usual thing you're familiar with qubits. And the important thing is that this set of operators, x to the power a, z to the power b, where a and b range over the index dimension of the dimension, that these form a basis. Like in the previous slide, I talked about this basis, B alpha. So this set of Heisenberg-Weyl operators forms a basis for the operator space. So all of the results I'll talk about leverage this basic fact. So simplifying the case of QuDits, I want to talk a bit about errors and the different types of errors. So I want to emphasize the importance of coherent versus decoherent errors. So a coherent error we can think of as some small over-rotation. Here, let's look at the z-axis for simplicity. And so the usual unitary 2x2 matrix is shown here, where it's diagonal because it's a z operation. And you look at the superoperator and you see that rotation. Notice that the lower 3x3 matrix in the lower right-hand side of this matrix is just the SO3 rotation, the standard rotation in Euclidean space, corresponding to the rotation of the qubit. But what's really important to realize is if we think of theta as a small error, then we can expand out these terms, and the off-diagonal term goes linearly with theta, and the diagonal terms go quadratically. So what this tells you is that if theta is, say, 10 to the minus 2, the size of the matrix elements, the errors in this matrix, are 10 to the minus 2 on the off-diagonal, but 10 to the minus 4 along the diagonal. So a big theme of my research in the past decade has been focused on strategies to get rid of those off-diagonal terms, so we're getting basically a quadratic improvement in the error reduction. So an important class of channels are stochastic channels, which are normally thought of as just a linear combination of Pauli errors, where we have a discrete probability over the set of possible Pauli errors. And this, of course, generalizes to Heisenberg-Weyl operators. The point is then there's no cross terms in the chi matrix. The Pauli error rates, this p alpha, is just a vector of errors, of error rates. Depolarizing case corresponds to a highly degenerate situation where there's one independent parameter, p, which is essentially the probability of the identity term, and everything else has a probability of 1 minus p divided by d squared minus 1 terms. This kind of very mathematically beautiful and simple error model is not very physically natural. Physical errors tend to have off-diagonal terms. For example, finite precision drift of analog control will lead to typical off-diagonal terms. But if we just go back to this mathematical hypothetical and we think about these Pauli error channels, then the Liouville matrix, or the Pauli transfer matrix I mentioned earlier, just is a diagonal matrix with a set of eigenvalues. And what you can see is that those eigenvalues are related to the probabilities of the different Pauli errors through a simple relationship based on the commutativity of the Paulis. And here we have all of the power of linear algebra to understand this. So the other thing we realize is when you look at this equation, there's the pointer, right? This equation here, you realize that, well, if I input a Pauli operator, then this diagonal Pauli matrix is just going to give me the eigenvalue associated with that Pauli matrix. So that's a key idea that's going to allow us to learn about that error model. So let me talk a little bit more about figures of merit. So there's the average gate fidelity at the top. The error rate, or the randomized benchmarking number, is just 1 minus that average fidelity. People also talk about norms that differentiate the error process from the identity map. And a common one is the diamond norm. For example, it's used in fault-tolerant proofs. And I won't give a formal definition because it's a bit clumsy, but you can think of it as a worst-case error, which is essentially picking up on the worst-case off-diagonal terms. And then another interesting figure of merit for error is this total variation distance, or the L1 norm, between the output probability distribution in the ideal case versus the error-prone or experimental output distribution. And there you just sum over the absolute value of the differences of those two probabilities across bins. So let me just review something which people know well, which is the standard kind of randomized benchmarking scheme. The idea is you imagine a sequence of gates, G1 through GM, and each one has an error associated with it. And it turns out if these G1 are chosen from, say, Haar random unitaries, then you can prove there's an exponential decay, where the exponential decay depends on this depolarizing probability of the noise. So using random unitary operators for that is not ideal. Manny-Nil proposed using a subset of the Cliffords, but that turns out it isn't invariant. And so later in my work with Richard Cleave here, led by his student Dankert, and then later with Jay and Iswar, we put out a more general theory based on uniformly sampling from the Cliffords, which is cleaner and easier to implement because Cliffords can be implemented with efficient circuits, whereas Haar random unitaries require exponentially long circuits. So that allows it to scale up. So for 2-qubit gates, you would use something called a unitary 2 design, which it turns out the Cliffords are for qubits. It turns out the Cliffords are not a unitary 2 design in all dimensions. Kind of depends how you define the Clifford group, and there's some subtleties there. But for power of odd prime, for power of all primes, of qudits, your prime dimensional qudits, this applies. And so the idea is you apply this inverse operation and you measure the decay rate to get the error rate per Clifford. And then there's a scheme proposed by Iswar when he went to IBM called interleaved RB, where you implement G, which is some gate of interest, in between the randomizing gates, and then you can isolate the error on that target gate of interest like a C0. There are some problems with interleaved randomized benchmarking, which is that the random unitary you're applying between the target gates can have a much bigger error than the error you're trying to isolate on the distinguished gate G. So what we proposed more recently is a cycle benchmarking method where instead of using a unitary 2 design, you just use random Paulis and you apply your gate of interest. And this allows you to measure the error rate of this gate of interest to much higher precision. And so the scheme is basically you prepare some input state, which I'll talk about later. You apply random Paulis on each qubit, or random Heisenberg-Weyl operators. We're doing this for QuDits. You apply your 2-qubit to QUDIT gate, and random Heisenberg-Weyl operators, and so on. And just to showcase some of the advantages of this, we did some experiments comparing IRB, which is what kind of IBM uses and is typical, to this cycle benchmarking approach using the weaker twirl, using polys. And in blue here is the cycle benchmarking results, and in black and gray is the IRB results, depending on whether you use Clifford's or SU4 randomizing gates. And what you see here is these upper triangles denote the systematic error. So it turns out, if you're just trying to measure the error on that gate and you're twirling it with some big Clifford, you can have some large coherent error, and you don't know if that large coherent error is partially canceling the error on your gate of interest. And so the larger the error on the twirling gate, the bigger the possible cancellation, which means you have, in addition to your statistical uncertainty, which is shown with error bars, you also have a systematic uncertainty in identifying the error of that gate. And here you see the statistical uncertainty is much smaller for cycle benchmarking, and the systematic uncertainty is also much lower. So when experimental groups do IRB, they report this number with this error, and they don't report this number, which is unfortunate because it turns out this is the worst case for your gate performance. So you're talking about sometimes an order of magnitude loss in potential precision. You could be unlucky if that's the case, but if you want to be precise and rigorous, a better way to do it is to use cycle benchmarking. Okay, I'm going too slowly. Let me talk about randomized compiling now. So again, think about this simple error model of a coherent over-rotation due to, say, drift in your control. Then it's important to realize that under randomized compiling, what it's going to do is it's going to reduce this error model to a diagonal stochastic channel. And the reason that's interesting is because if you're not guaranteed your error is stochastic, the diamond norm, which upper bounds the variation distance, so this is how you calculate the variation distance, goes as square root of the error rate you measure via randomized benchmarking. So if you say, oh, I'm doing great, I have 10 to the minus 4 errors, well, it turns out your diamond norm, which is relevant, say, to fault-tolerant thresholds, is really 10 to the minus 2. But if you do randomized compiling, you can kill off the off-diagonal terms, and now the diamond norm is upper bounded by something that's linear in R, so you recover your 10 to the minus 4 instead of this 10 to the minus 2 upper bound. That's the kind of the main idea behind why randomized compiling is helpful. You get rid of these off-diagonal terms, and so your potential for really bad errors goes away. So the way you do randomized compiling is you take some native circuit, you insert virtual gates on your QuDits, and then you have your hard gate, and you insert more virtual gates before and after every hard gate. Then you compile all these together, and you get a new local gate. And then you have the same circuit, but you've changed the local gates. And you do that ideally every time you run a new shot, although in practice people don't like reloading the FPGA, so you maybe run 100 shots and then change the circuit to these new local gates. And that gives you the effects I talked about on the previous slide. Here's a more kind of technical description of what's going on, where people often confuse randomized compiling with polyframe randomization, which Manny Nil proposed, but it's different. Polyframe randomization only works for Clifford circuits, so it doesn't work for universal circuits, but randomized compiling works for universal circuits due to this extra correction gate which we apply to keep the errors from spreading throughout the circuit. And this method works for prime dimensional Qudit systems. It might work in non-prime dimensional Qudit systems, but that requires some more analysis. So here's a canonical scenario. You would take your easy gates, the C gates, as the Clifford single qubit or single Qudit Cliffords. Well, I guess this is just specific to qubits. You would take the phase gate and the polys as your generators of the easy gate set, and then you treat the Hadamard, the T gate, and the 2-qubit Clifford as your hard gates, and then the randomizing gates are polys, and then the correction gate ends up being part of the easy gate set, which is the Cliffords. So in this way, you can apply randomize. You can remove the off-diagonal terms in universal circuits. So just to showcase how it works, just some old numerics that show that if your error is already stochastic because of whatever misfortune, Dephasing errors, by the way, are stochastic. So that is kind of a natural way to get stochastic errors. So if your errors are really truly only dephasing, for example, then randomized compiling doesn't help. But if you have coherent errors due to drift and so on, crosstalk, then you get a big reduction in your effective error from randomized compiling. This was just to show that the number of different randomized realizations of the circuit you have to average over maxes out at about 20, and that's actually independent of the system dimension. Here's some experimental work at Berkeley where they implemented this scheme and they show the reduction in error due to randomized compiling. I'll just skip over those details and talk about now the idea of cycles in the context of error characterization as well as randomized compiling. So you're going to divide your circuit up to an alternating sequence of easy and hard gates based on that canonical breakdown I gave earlier. And then you average over randomizing the easy gates. And that gives you essentially a fixed circuit structure with, we call this a dress cycle. So the hard gate round, which is typically your 2-qubit gates, or your T gate, which are expected to have much higher error rates, combined with your easy gates, which typically have much lower error rates. And one of the things we really want to emphasize is because we've realized so many systems have a crosstalk problem, it's not enough just to do component benchmarking and look at the error rates of your C0 and so on, because doing the C0 can induce errors on the idle qubits. So really you need to understand the error profile across the entire register of qubits during one time, during one moment or one clock cycle of operations. And so the cycle benchmarking scheme I described earlier generalizes to the n QuDit setting. So I have n QuDits. As long as they're prime dimensional QuDits, this all works based on a canonical decomposition for universality. And you prepare a local state, which is basically a Pauli operator. You apply a randomization. You apply your parallel instruction set, which is some parallel set of say, C0s or C-sum gates for QuDits. And then you apply your randomizing gates. You repeat that m times to amplify the error. And what you can do from that is measure, let me skip the non-Clifford example. You can measure like what we call the cycle fidelity. So it's essentially the error rate across the entire n qubit or QuDit register. So here what we did back in 2019 is we took all 6 different allowed parallelizable 2-qubit operations on this T gate, this T architecture that IBM had. So they had 6 different systems, all with the same T architecture, and depending on the fab process, all of these were basically the same design, but very different instances in terms of performance, I think due to variations in fab. And these are the different names. And we basically measured the cycle fidelity or infidelity of each parallel instruction set that was allowed by connectivity for each of these processors. And you see this huge spectrum of performance. And what I'm not showing there is how you can't predict that error rate from the component benchmarks due to crosstalk. And what I wanted to say is that now beyond measuring the fidelity, we can also measure the individual eigenvalues. So this is something we call cycle error reconstruction. I'll skip. But basically the idea is you prepare some input Pauli, or identity plus that Pauli. You apply your randomized cycle benchmarking circuit, and then you measure that Pauli, and that gives you the eigenvalue associated with that specific Pauli. Thank you. So with that scheme, you can achieve to multiplicative precision the errors on these eigenvalues, which transfers to high precision measurement of the Pauli error rates themselves. There are some degeneracies. Here's an example of us running this experiment. This is from 2018, unpublished, with Innsbruck on their ion trap. This is a qubit experiment, unfortunately. But here we'll reconstruct the probabilities of all these different possible errors across a 4-qubit system. And so this is very powerful for diagnosing kind of an error model you might have for your control and understanding where things are going wrong, how to improve it. More recently, and I don't talk about this work in this talk, but I've been working with Pavithran Iyer and Aditya Jain and Steve Bartlett to understand how to input this information into a heuristic, which can feed into a decoder, and it delivers up to 10 times better performance of the decoder, 10 times better logical error rates by informing the decoder of this error model so that it can make the best possible inference about the syndrome. In this case, this is the data for just doing the identity hard gate, which is not very hard, and then this is doing the MS gate across the 4-qubit system. So very different error profiles, including lots of high weight errors induced by the MS gate. This is their old-fashioned way of doing the MS gate. Here's diagnostic data we obtained on IBM, and we saw a very strong crosstalk. Oh, no, sorry, that's Innsbruck again. IBM's on the next slide, where we saw a very strong crosstalk in IBM's cross-resonance gate. IBM's now moved away, my understanding is, from the cross-resonance gate to tunable coupling because of the problem of this crosstalk problem. Last but not least, I'll skip all these words and just say out loud what the problem is, and it's what I mentioned at the beginning of the talk. How do you get a sense of how much you can trust the answer of some dynamical simulation or some quantum chemistry problem you're studying with a quantum computer? And so we actually have a pretty good answer for this. The idea here, phi is the symbol that Arnaud uses for the process fidelity of a cycle. And basically, in this paper with Arnaud, what we showed is that if you have a circuit composed of m sequential cycles, hard gate cycles, or addressed hard gate cycles, then the fidelity of that circuit, which is your application, some depth 100 circuit, can be well approximated by the product of the cycle fidelities of each of those components. So this is very counterintuitive, and to derive this, we have to make an assumption on the error model. First of all, that it's twirled, so it's stochastic, and second of all, that it's what we call non-catastrophic. So there we're ruling out very, very unphysical error cases for which this theorem doesn't hold, but we also argue they're unphysical. So the kinds of things where this breaks down is if your error was, if on n qubits, control, 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 control u. Something very, very highly contrived like that, this result would not hold. And basically the idea is then we can predict the fidelity of the whole circuit based on the fidelity of the components. What this also means is kind of like bad news for the quantum cloud providers, because it's basically saying, if we just measure the fidelity of each of your cycles and create a repository online of that, then we can actually predict how the accuracy with which you can run any algorithm on any processor and bound, first of all, the fidelity of that processor. But more importantly, with that fidelity bound, we can, if we're using randomized compiling to implement the algorithm, we can apply this infidelity bound on the full circuit, which is what I just showed you here, this fidelity bound. We can use that, and this is unpublished and very cutting edge here, and this is just order 1. We can use this bound to bound the diamond norm of the error across the full computation to the identity, which then also bounds the TVD, which is the difference between the experimental probability distribution and the ideal probability distribution. And then we've worked out examples, for example, in simulating spin systems, where this gives a very accurate bound on the total performance of the quantum processor to run that simulation. So for typical numbers, we can show, for example, that your ability to measure the total polarization of your spin system is accurate to within 10% by measuring this component information. So we're very excited about seeing how that result can play out. Here's all the equations put together on one slide. And also, I'm saying here, we could also use this to do a scalable quantum volume. I'm running out of time, so I won't tell you the details. You can ask me in questions about it. And with that, I will, hopefully that's my thank you slide. Yes, perfect.